We're now equipped to return to our original question. We have the Earth, we have the density function as a function of the density as a function of rho. We've seen why that's what we would expect. Of course, we haven't gone deeply into the geology of the Earth and the formation and so forth, but that's very much related to the actual density function. So we're trying to find the moment of inertia of the Earth about its central axis, and that would be the same as the moment through any axis through the center of the Earth. In spherical coordinates, we take a sample point rho I star, theta j star, phi k star, and we ask what happens in the neighborhood of that point. We define a volume increment by delta rho, delta phi, delta rho, delta theta, delta phi. We have our density evaluated simply at the rho sub I star sample point. What's our volume increment? Well, we've now seen that our volume increment is rho I star squared times the sine of phi k times what? Delta rho, delta phi, delta theta. So that the mass of our ijk sample interval is what? It's the product of density and volume. That's going to be 12 minus 9 over r rho sub I star multiplied by our volume increment, which is rho I star squared sine phi k star, should have a star on it here, times delta rho, delta theta, delta phi. And these increments can be written for now in any order. The order in which we actually present them when we express this as an integral will depend on how we describe the region. Turns out that in this case it's not going to make much difference at all. We have our expression for the mass contribution of an interval defined by delta rho, delta phi, delta theta, delta phi in the neighborhood of the sample point, rho I star, theta j star, phi k star. The entire sphere of the Earth is characterized by the fact that its distance from the center is less than or equal to its radius. So that rho, the rho coordinate, if we identify the center of the circle with the origin of our coordinate system, rho can go from 0 to r. Okay, so the sphere is zero less than or equal to rho less than or equal to r, where the coordinate system has origin corresponding to the center. What about theta and phi? Well, theta, if we look at our typical rho theta phi point here, if theta goes from 0 to 2 pi, this point here will travel around a circle. And if we then let phi go from 0 to 2 pi, our circles will start out small, expand, then contract in such a way as to describe the entire sphere. So the sphere can be written as 0 less than or equal to rho less than or equal to r, 0 less than or equal to theta less than or equal to 2 pi, and 0 less than or equal to phi less than or equal to pi. Our information can therefore be summarized. Our delta Mij is the expression we obtained previously, just our density at the ijk sample point times the volume increment at the ijk sample point. The sphere described by the inequalities we've seen, so that when we sum up our mij, we partition these intervals: 0 less than or equal to rho less than or equal to r, 0 less than or equal to theta less than or equal to 2 pi, 0 less than or equal to phi less than or equal to pi. We partition these intervals. Our sum of mij, well, we're going to sum that over 3 intervals with respect to 3 variables. Okay, so we're going to do like a triple sum of mij. Without writing out the details of that, this triple sum will approach a triple integral. Depending on the order in which we write this out, we could write this triple integral in any of a number of ways. The 3 sums correspond to the 3 partitions, and it should be then clear that one of our partitions will go from 0 to r with respect to rho, and we can hang on a second, excuse me, we can integrate from 0 to r with respect to rho, from 0 to 2 pi with respect to theta, from 0 to pi with respect to phi. Quantity we're going to integrate, well, in the first place we're going to need a rho squared sine phi to complete our volume increment. And I'm not going to be able to get that in with a marker, so I'm going to switch to a fine point here. So we're going to have a rho squared sine phi that'll complete our volume increment, and then we have our density function, which is 12 minus 9 over r multiplied by rho. I started the parentheses with the green marker, so I'll finish it that way. When we multiply out all the terms of this integral, we find that the volume is going to be the integral from 0 to pi. I'm sorry, not the volume, the mass is going to be integral from 0 to pi, integral from 0 to 2 pi, integral from 0 to large R of what? It's going to be 12 minus 9 over large R. Times rho cubed, rho times rho squared, sine phi, d rho, d theta, d phi. Now I've just noticed that what I've got here doesn't make any sense at all, because I wrote something down carelessly way back here. The density is 12 minus 9 over r rho sub I star, not the quantity 12 minus 9 over r times rho sub I star. Okay, I've made some repairs here. This expression should be 12 minus 9 over r times rho I star. Remove the parentheses in here, and I've done similar pairs here, here, and here, so that now these expressions should be properly ordered. Now this integral is going to be very easily performed. We simply expand the polynomial here. We get 12 rho minus 9 rho cubed over big R with respect to rho, just a polynomial. Then we're going to just integrate. We have no theta dependence in our rho limits, so we're just going to integrate theta from 0 to 2 pi. That's just going to give us 2 theta. And then we integrate the sine of phi with respect to phi between 0 and pi, and the result's simply going to be 1. Actually, that result will be -1, but we're going to get a negative when we integrate our rho function. Now, that's not true at all. R is a big denominator. This term is going to be bigger than this one. And our antiderivative of sine theta will be the negative of the cosine evaluated between 0 and pi. Will give us a positive 1. We'll get a volume. I'm sorry, this won't be a volume. This will be an integral for our mass. Now, remember, we're ultimately trying to find moment of inertia. But first, we're going to do this mass integral, and then we'll see how easily we can modify this to get our moment of inertia integral.